Weld defects and quality control. Non-destructive testing methods. 1. Testing and inspection methods. Tests must be made to qualify the process and the operators. Inspection usually involves the examination of completed welds to establish their quality and their conformation to specifications. Thus, testing and inspection determines whether or not the quality standards of materials and workmanship are being met. In welded joints, the complexity is further increased by the nature of the joint, which is far from homogeneous, metallurgically or chemically. In addition to the base metal, the welded joint consists of weld metal and a heat-affected zone. A variety of properties are thus to be expected throughout the welded joint. Mechanical tests are used to qualify welding procedures, welders, and welding processes, and to determine if electrodes and filler metals meet the requirements of the specification. Welds in weldments are often tested for soundness, strength, and toughness by mechanical tests. Mechanical tests are destructive tests since the weld joint is destroyed in making the test. The test specimen coupon may be taken from a completed joint in a welded structure or from a test piece welded at the same conditions. 2. Testing and inspection methods. Destructive tests. Tension test. Nick break test. Bend test. Hardness test. Fatigue test. Impact test. Non-destructive tests NDT. Visual examinations. Radiography testing. Gamma ray. X-ray. Magnetic testing. Ultrasonic inspection. Penetrant examinations. Stethoscope test. Eddy current inspection. 3. Visual inspection. It is the most widely used non-destructive testing technique. It is extremely effective and is the least expensive inspection method. The welding inspector can utilize inspection visual inspection throughout the entire production cycle of a weldment. It is an effective quality control method that will ensure procedure conformity and will catch errors at early stages. Visual inspection methods can be divided into 3 groups. Visual examinations prior to welding, drawings, material specifications, edge preparation, dimensions, cleanliness of the welding joint, etc. Visual examination during welding, welding process, electrode selection, operating conditions, preheat requirements, welder performance, etc. Visual examinations of the finished weldment, weld size using weld gauges, defects, surface cracks, creator cracks, surface porosity, incomplete root penetration, undercut, underfill, warpage, base metal defects, etc. 4. Non-destructive testing methods. Ender may be used to reveal defects that would be difficult or impossible to detect by visual examination. The techniques are used during manufacture as a quality control tool to determine the quality of the work. The extent of Ender depends upon the application and the criticality of the joint and is generally specified in the relevant application standards or contract specification. It is important for Ender to be included in the planning of the fabrication process as it can require substantial time and resources. Full account of this must be taken if disruption of production and delays to the program are to be avoided. 5. Non-destructive testing NDT. Non-destructive testing is also known as non-destructive examinations or evaluation Ender, or inspection. These techniques use the application of physical principles from the detection of flaws or discontinuities in materials without impairing their usefulness. In the field of welding, 4 non-destructive tests are widely used: dye penetrant testing and fluorescent penetrant testing, magnetic particle testing, ultrasonic testing, radiographic testing, weld penetrant examination. Liquid penetrant examination is a highly sensitive, non-destructive method for detecting minute discontinuities, flaws, such as cracks, pores, and porosity, which are open to the surface of the material being inspected. It may be applied to many materials, ferrous and non-ferrous metals, glass and plastics. The applied surface must be cleaned from dirt and film. So, discontinuities must be free from dirt, rust, grease, or paint to enable the penetrant to enter the surface opening. A liquid penetrant is applied to the surface of the part to be inspected. The penetrant remains on the surface and seeps into any surface opening. The penetrant is drawn into the surface opening by capillary action. The parts may be in any position when tested. After sufficient penetration time elapsed, the surface is cleaned and excess penetrant is removed. The penetrant is usually a red color, therefore, the indication shows up brilliantly against the white background. Even small defects may be located. A penetrant examination. This is a technique that is capable of detecting surface breaking defects only. It relies upon a colored or fluorescent dye sprayed upon the surface, penetrating these defects. After cleaning the excess from the surface, the dye within the defect is drawn to the surface by spraying on a developer in the case of the color contrast dye, or by exposing the surface to ultraviolet light. The defect is revealed by the dye staining the developer or by fluorescing. The dye used as a penetrant must be capable of penetrating narrow cracks, but must not be removed from more open defects. During the cleaning operation carried out before the application of the developer, the dye must have a high contrast with the developer. It is important that the test piece is thoroughly pre-cleaned. Any dirt, oil, or water in the crack may prevent the penetrant from entering. Degreasing should be carried out by swabbing or immersing the item in one of the proprietary cleaners, acetone or methanol. 8. Weld penetrant examination. Applications. Liquid penetrant examination is used to detect surface defects in aluminium, magnesium, and stainless steel weldments when the magnetic particle examination method cannot be used. 1. 2. It is very useful for locating leaks in all types of welds. Welds in pressure and storage vessels and in piping for the petroleum industry are examined for surface cracks and for porosity. Fluorescent penetrant examination. The penetrant is fluorescent, and when it is exposed to ultraviolet or black light, it shows a glowing fluorescent type of readout. It provides a greater contrast than the visible dye penetrants used for leak detection in magnetic and non-magnetic weldments. A fluorescent penetrant is applied to one side of the joint, and a portable ultraviolet light is then used on the reverse side of the joint to examine the weld for leaks. Inspect the root pass of highly critical pipe welds. 3. 4. 1. Section of material with a surface minus breaking crack that is not visible to the naked eye. 2. Penetrant is applied to the surface. 3. Excess penetrant is removed. 4. Developer is applied, rendering the crack visible. 10. Advantages. It can be used on both ferrous and non-ferrous metals. It is very portable. Large areas can be examined very quickly. It can be used on small parts with complex geometry. It is simple, cheap and easy to use and interpret. Disadvantages. It will only detect defects open to the surface. Careful surface preparation and cleanliness are required. It is not possible to retest a component indefinitely. There may be health and safety problems with some of the chemicals. There are health and safety problems with fumes in confined spaces. 11. Magnetic particle testing. This method is mainly used for assessing the surface and near-surface defects in magnetic material. It is based on the simple principle of the flow of magnetic line of forces. Magnetic flux flows easily through metal from south to north pole. The component to be evaluated is magnetized using electrical energy or suitable permanent magnetic. The electromagnetization is performed using suitable yoke which is applied across the location/area to be tested. Presence of any discontinuity in the form of crack, porosity, near-surface defects in the path of flow of these lines results in leakage of magnetic flux forming to additional poles. The magnetic powder particles in dry form or suspension form in thin liquid are sprinkled over the surface of components to be tested. The magnetic particles tend to migrate towards the location wherever leakage of magnetic flux had taken place and then get piled up. Fig. 32.9. The particles align along discontinuities on the surface, near or shallow subsurface discontinuities. The location and pattern of piled up magnetic powder particles suggest the location, size, type of discontinuity present on the surface or near surface region. Hazy pile of powder particle. 12. Flux leakage. S. N. N. S. Indicates the subsurface defect. Formation of very thin line of powder particles suggests presence of crack with details of size and location of crack. However, this method of testing is found fit for ferromagnetic metal only. Fig. 32.9 Principle of magnetic particle test. Eddy current examination. Eddy current examination is a process that may be used on any material that will pass an electric current. A coil carrying an alternating current is placed close to the item to be examined, inducing an eddy current in the specimen. Defects in the specimen will interrupt this eddy current flow, and these perturbations can be detected by a second search coil. The coils can be placed either side of a thin plate-like sample or can be wound to give side-by-side coils in a single probe. These may be shaped to fit in the bore or around the outside of pipes and tubes, and in these applications the process lends itself to automation. The equipment is calibrated using a defect-free specimen. The accuracy can be affected by metallurgical condition, standoff and coil dimensions. For these reasons, eddy current testing is used only rarely on welded components, although it is excellent in examining continuously welded tube from pipe mills. 14. Eddy current testing. Eddy current testing. Coil. Eddy. Currents. Coils. Magnetic field. Eddy currents. Magnetic field. Conductive material. In eddy current testing, a coil carrying an AC current is placed close to the specimen surface or around the specimen. The current in the coil generates circulating eddy currents in the specimen close to the surface, and These in turn affect the current in the coil by mutual induction. Flaws and material variations in the specimen affect the strength of the eddy currents. The presence of flaws, etc., is therefore measured by electrical changes in the exciting coil. Both voltage and phase changes can be measured, but some simpler instruments measure only the voltage changes. 15. Features of process. The accuracy can be affected by metallurgical condition, standoff, and coil dimensions. For these reasons, eddy current testing is used only rarely on welded components, although it is excellent in examining continuously welded tube from pipe mills. The process has been developed over recent years to make it more portable and simpler to use. Microprocessor-based control and recording units, improved and more tolerant probes and lightweight electronics have enabled the technique to be used on site for the examination of structures in service, where it is an effective tool for the detection of cracking and corrosion problems. It is also possible for the depth of surface cracks to be determined. It is of limited use for interrogating welds, however, being most commonly used in the examination of continuously welded tubes. 16. Ultrasonic examination. The ultrasonic examination of welds uses the same principles as when sonar is used for the detection of submarines. A sound wave emitted from a transmitter is bounced off an object and this reflection captured by a receiver. The direction and distance of the object can be determined by measuring the elapsed time between transmission and detection of the echo. In welded components, this is usually done by moving a small probe, containing both transmitter and receiver, over the item to be examined and displaying the echo on an oscilloscope screen. The probe transmits a beam of ultrasound that passes through the metal and is reflected back from any defects. Much like shining a torch at a mirror, in principle, with the same rules applying to the reflection of the beam. This is illustrated in Fig. 17. Initial, pulse, crack, echo, back surface, echo. 0246 of August 10. Oscilloscope or floor. Detector screen. Plate. Crack. Ultrasonic examinations. Deeply buried defects such as lack of fusion, lack of penetration and cracks in addition to volumetric defects such as slag entrapment and porosity are all easily detected. The frequency of the ultrasonic waves is generally in the range of 2–5 MHz, the lower frequencies being used for the examination of coarse-grained material and on rough surfaces. The higher frequency probes are used for the detection of fine defects such as cracks, non-minus metallic inclusions, lack of fusion, and voids. 18. It is a non-destructive examination method that employs mechanical vibrations, similar to sound waves, but of a higher frequency. A beam of ultrasonic energy is directed into the specimen to be examined. This beam travels through a material with only a small loss, except when it is intercepted and reflected by a discontinuity or by a change in material. Ultrasonic examination is capable of finding surface and subsurface discontinuities. The system uses a transducer, which changes electrical energy into mechanical energy. The transducer is excited by a high-frequency voltage that causes a crystal to vibrate mechanically. The crystal probe becomes the source of ultrasonic mechanical vibrations. These vibrations are transmitted into the test piece through a coupling fluid, usually a film of oil, called a couplant. When the pulse of ultrasonic waves strikes a discontinuity in the test piece, it is reflected back to its point of origin. The transducer serves as a receiver for the reflected energy. The initial signal or main bang, the returned echoes from the discontinuities, and the echo of the rear surface of the test material are all displayed by a trace on the screen of a cathode ray oscilloscope. 19. Equipment: transducer, pulse rate generator, amplifier, timer, and cathode ray oscilloscope. All are portable. Applications: practically any metal or material. Restricted only very complex weldments and joining of plates with thicknesses of 10 mm to 12 mm or more. Cracks, gas pockets, and slag. Advantages: it is very good for the detection of planar defects and cracks. It can easily determine defect depth. It is readily portable. Access is required to one side only. There are none of the health and safety problems associated with the radiographic technique. Disadvantages: very skilled operators are required. Surface breaking defects are difficult to detect. Accurate sizing of small 3 mm defects is difficult or impossible. The geometry of the joint can restrict the scanning pattern and prevent accurate interpretation. No permanent objective record is available. The process can be slow and laborious. Radiographic examination. 23. Electromagnetic radiation has properties that are useful for industrial radiography purposes. The rays travel in straight lines and cannot be deflected or reflected by mirrors or lenses. They have wavelengths that enable the radiation to penetrate many materials, including most metals. They will, however, damage living tissue and therefore present some health and safety problems. The radiation, either X-rays from a suitable source or gamma rays from a radioactive isotope, is absorbed as it passes through the material. This absorption increases as the density of the material increases, so that if a photographic film is placed on the side opposite the radiation source, any less dense areas will appear as darker areas on the film to give a shadow picture of the internal features of the test sample once the film has been processed. Thus voids, porosity, slag, cracks and defects of geometry can all be identified, although planar defects normal to the beam may not be detected. Radiographic examinations. Radiography is a non-destructive examination method that uses invisible X-ray or gamma radiation to examine the interior of materials. It gives a permanent film record of defects that is relatively easy to interpret. Although this is a slow and expensive method of non-destructive examination, it is a positive method for detecting porosity, inclusions, cracks, and voids in the interior of castings, wells, other structures. X-ray generated by electron bombardment of tungsten, and gamma rays emitted by radioactive elements are penetrating radiation whose intensity is modified by passage through a material. The amount of energy absorbed by a material depends on its thickness and density. Energy not absorbed by the material will cause exposure of the radiographic film. Those areas will be dark when the film is developed. Areas of material where the thickness has been changed by discontinuities, such as porosity or cracks, will appear as dark outlines on the film. All discontinuities are detected by viewing shape and variations in the density of the processed film. 25. Applications. It is used for examination of weldments in all types of materials. Pipeline industry to ensure proper weld quality. Radiation source. Photographic film. A. 27. Fault shown on exposed film. Advantages. A permanent record is available. Both buried and surface defects can be detected, and the technique is particularly good for finding volumetric defects, such as slag and porosity. The equipment is portable, particularly the gamma ray sources. All materials can be examined. Disadvantages. The capital cost of equipment, which will need to include the processing and viewing facilities. Health and safety considerations. Large areas may need to be closed off during radiography, or enclosures must be provided in which the radiography is carried out. Radiographers must also be monitored for exposure to radiation. Access is required to both sides of the component, the source on one side, the film on the other. There are problems in detecting planar defects and fine cracks if these are normal to the beam. There is a limitation on the thickness that can be radiographed and defects easily detected. Skilled and experienced radiographers are required. The depth and through thickness dimension of a defect is very difficult to determine. 28. Examination technique. Visual, VT. Dye penetrant or fluorescent, DP, effort. Magnetic particle, mount. Radiographic, RT. X-ray or gamma ray. Source film processing. Equipment, film. Viewing equipment. Penetrometers. Ultrasonic, UT. Equipment. Pocket magnifier. Welding viewer. Flashlight, weld gauge. Scale. Fluorescent or visible. Penetrating liquids and developers, ultraviolet light for the fluorescent type. Iron particles, wet or dry, or fluorescent. Special power source. Ultraviolet light for the fluorescent type. Ultrasonic units and probes, reference and comparison patterns. Defects detected. Weld penetration, fit up. Cleanliness, roughness. Spatter, undercuts. Overlaps, weld contour. And size, welding. Procedure. Defects open to the surface only, good for leak detection. Surface and near surface. Discontinuities, cracks, etc., porosity, slag. Most intermal. Discontinuities and flaws. Limited by direction of discontinuity. Can locate all internal flaws located by other methods with the addition of exceptionally small flaws. Advantages. Easy to use, fast. Inexpensive, usable at AI stages of production. Detects very small, tight surface imperfections, easy to apply and to interpret. Inexpensive, use on magnetic or non-magnetic materials. Indicates discontinuities. Not visible to the naked eye, useful in checking edges prior to welding. Also, repairs, no size restriction. Provides permanent record, indicates both surface and internal flaws, applicable on all materials. Extremely sensitive, use restricted only by very complex weldments, can be used on all materials. Disadvantages. For surface conditions only, dependent on subjective opinion. Inspector. Time consuming in the various steps of the process, normally no permanent record. Used on magnetic materials only, surface. Roughness may distort magnetic field, normally no permanent record. Usually no suitable for fillet weld inspection, film. Exposure and processing critical, slow, and expensive. Demands highly developed interpretation skill. Other considerations. Most universally used examinations method. Often used on route pass of highly critical gas wells if material improperly cleaned. Some indications may be misleading. Examination should be from two perpendicular directions to catch discontinuities that may be parallel to one set of magnetic lines of force. Most popular technique for subsurface inspection, required by some codes and specifications, required by some codes and specifications. 29, 19.